This course that we're starting is part of the straight line training concept, where we identify the target, the destination, we identify the starting point, we draw a straight line between the two, and we try to catch everything on the way. So far we did what does a PLC do, that puts you in the picture. We talked input devices, output devices, and then we talked hardware, which is what you connect up the inputs and the outputs to. Then we talked about what's in the PLC, the controller processor and its memory, ladder logic diagrams. Then we kind of dropped back to the 1,000-foot view and looked at the entire scope of what is a PLC. So at this point, you should be in a good mood to learn the rest of this course. However, there's one more thing that we need to do before we jump into the course, and that is talk about what you want to use for a controller. There's two ways you can go, hardware or you can use the simulator. Connected Components Workbench, starting with version 12, has a simulator, and it works really good. It does fault on occasion, and it'll say watchdog timeout. And you have to remember that if you had a computer permanently set aside just to run CCW in the simulator, you could probably set it up so it would never fault, primarily by reducing the number of processors in the details for CCW or the simulator. Don't increase the watchdog timer, because that's not the issue. I noticed it defaults quite often if I'm working with two screens and going back and forth, or if it goes into screensaver or the computer goes to sleep. So it's real simple. If it faults and you're still connected, just go up to diagnose and clear the fault and keep on going. Now when you clear the fault, it's going to leave it in the program mode. You're going to have to put it back in the run mode and back in remote. Or if it's not connected, then you go back to your program offline and download it. That puts a serious attention on whether or not you save your program enough. So in this little session, we're going to talk about building a Micro 800 learning station, meaning you purchase a Micro 800, you buy some lights and switches, power supply, and whatever other doodads and foo-foo geejaws you want to add to your Space Cadet learning station, and you start soldering, screwing, and put it together. Then you start doing the lab projects in the course. Or you could just use the simulator. Now the lab project manuals we're using were originally written with Micro 800 hardware controllers, specifically the 820, 850, and 870. I did do some with the 810, but the 810 I abandoned it really quick because it's just starved for features and friendliness for what we're doing. So you can use a hardware controller to do the lab projects or the simulator. And in the sessions you're going to be watching from here on out, they were all done for the most part with a simulator, simply because I wanted to make sure that the people that are using the simulator aren't left hung out to dry because I'm using a hardware controller. So I'm forcing myself to use the simulator in all the lab projects for the remainder of the course. From the PLCE University, from the Factory Rats Maintenance Workshop, let's build a learning station with the Micro 800. For those of you that don't want to use the simulator that comes free starting with version 12, release 12 of Connected Components Workbench, you can always build yourself a learning station with a Micro 800. My Micro 800 of choice is the Micro 820. The 810 is a entity all to itself. It's starved for features. It only has one COM port, doesn't have Ethernet. Let's take a look here. This is what we're going to build, or basically discuss building. This is a preview of it. Now let's get into it step by step. First of all, you need a controller, obviously. My controller of choice is the LC2020QBB, and it also has Ethernet. It also has RS-232, even though it doesn't have a conventional connector. So this is Ethernet. I put a little side view in there so you can see the Ethernet address, or MAC ID, but it has an Ethernet IP, which is a very important port, and then it's got an RS-232 485 port. So you have 6 terminals, and 3 terminals for 232, which would be pins 4, 5, and 6, and then 1, 2, and 3 are for 485. These are the screw terminals. Starting at the top, the input terminal strip is at the top. Terminal 1 is plus DC 10 volts. That's an output power supply for thermistors. You have 12 inputs. 4 of them, input 0, 1, 2, and 3, are shared between digital and analog. Inside of the box, the electronics supports those 4 terminals, 0, 1, 2, and 3, as a straight digital on-off, or they have an A to D converter, an ADC circuit. So you can configure those first 4 for analog inputs. Inputs 0, 1, 2, and 3 can only be used in syncing input configuration. And then these 4 inputs have a data range of 0 to 4095. That means it's 12-bit A to D conversion. And you're looking down at the bottom and you can see the value of the 12 bits. 12-bit is not high resolution. That means that your analog input will come in 4096 steps between 0 and 10 volts. Analog output. Now I know that the attribute output count range shows 0 to 4008. I could not find any explanation for that in the manual. I'm thinking it's 4095 just like the inputs. It's 12-bit. And it says 12-bit, 2.5 millivolt per count. That means as you run the analog value up and down, it goes in 2.5 millivolt jumps. So it starts at 0 and then to 2.5, then 5 millivolts, 7.5, nothing in between 2.5 and 5. It's in steps because this is converting from digital to analog. And there's only just the one analog output, and that's down at the bottom there, pin 4. This is a comparison between syncing and sourcing. Now remember the specifications for the 820, the QBB, is that the first 4 inputs are, and it says syncing only. What they mean is that the inputs can only sync from the sensors. Syncing is the half of the circuit that goes to common. So the source is 24 volts DC. In my case, it feeds all of the sensors. So look at the first 4 there on the top. They go to pins 3, 4, 5, and 6. You are sourcing the sensors and the input circuits, 3, 4, 5, and 6, which you can't see inside the plastic, that go back to pin 2, which is DC common. That is syncing the inputs. That's what they mean by syncing inputs. And there's always some confusion between sourcing and syncing because some manufacturers refer to their inputs based on what type of sensor you need and not the circuits inside of the controller. But Rockwell says these are syncing inputs, which means that the sensors have to be sourcing. Now, if you're using a dry contact like we're doing, it's irrelevant because dry contacts have no polarity. They're not polarity sensitive. So it really is not going to matter one way or the other. Where it will come into play is if you build a learning station and you use some of the practices that I do where I provide extra terminals for outputs or inputs that aren't connected to the simulators. In other words, they just go to a terminal block and then you can hook up your own sensors and output field devices for your own edification and learning experience. Then it matters because you have to know what you can do as far as syncing and sourcing goes. So if you compare the top set of terminal strips to the bottom, now these are both the input. These aren't the outputs. And the top one, the first 4 match the first 4 in the bottom one. They're sourcing only. Well, sourcing sensors, syncing inputs. For the QBB, the first 4 are syncing circuits only, which require a sourcing sensor. Now, you go to the other 8. You look at the top and notice that the minus is connected to pin 7 and the plus feeds all of the sensors. That's how I wire my digital field device simulators. It's all dry contact, so it really doesn't matter. On the bottom side, you see that it can support either. Notice that they have plus DC hooked up to common 0, and they're feeding all the sensors with the minus side of the power supply. The method of doing that is really outside the scope, but basically the opto isolator has 2 LEDs instead of 1. For the outputs, you have a variety of choices. Now, some of these outputs are high speed and some are not, but this shows you a possible circuit, and notice that we have the plus connected up to both commons. We're sourcing the loads, or you can say the loads are syncing. I threw this up here so you can see the current ratings on standard outputs, 0 through 5. And you can see that it's not high current. High speed output 6 is the high speed output. There's 1. That's 100 milliamps. Now looking at our wiring, the black wires are the common or the 0 volts. And up on top you see minus 24 volts DC. You see common 0, and the 6 terminal strip just below the big one, that's the RS-232 485. Go down the bottom and you can see power coming in for the controller. That's to the left, red and black. And then you have red going to the 2 positive commons and black going to the 2 negative columns. So that's your power connection. Power supply, you can buy a really nice power supply if you want. I prefer to buy these adapters. This is 24 volts DC output at 3 amps. You don't need 3 amps. 1 amp is more than sufficient. These power supplies or power adapters are typically $10 to $12 on either eBay or Amazon. Then, of course, you need something to plug it into. Now, the reason that I like plug into instead of screw terminals is you have less possibility of wires becoming twisted, fraying, and little flags sticking out and shorting to the other side of the supply. Now, I typically use 2 of these bulkhead connectors, and they are wired in parallel internally. That way I can plug into either one, and if I want to, I can have a jumper that goes from the box that these 2 are mounted in to another box with another bulkhead connector into it. That's typically how I build my field device simulators. Okay, input field devices. Now these are the large push buttons with LEDs in them. And if you're going to use something like this, you're going to need a larger box. But these are very inexpensive. Selector switch is the same thing as a toggle switch. There's different kinds of toggle switches. Center off, spring return to center, single pole, single throw, single pole, double throw, and so on and so on. So this, we'll just say this is a 2-position selector switch. Same thing as the toggle switches. I typically use toggle switches. This is I think it's a 16 millimeter. It's smaller. I showed you the back side of it so you could see that the 2 outside soldering lugs, if you look close, the one that you can see has a plus sign on it, and then on the far side you can't really see it, but hidden back there there's a minus sign. This is the LED. This is to power the light inside of it. Then you have 3 terminals for the push button. It's momentary. You have a common, normally open and normally closed. Output field device simulation. Remember that this was input, okay? Now the 2 on the bottom there, they are also have lights in them. And the one up in the upper corner, it has a light in it too. So the yellow terminal block on the back side of that one in the upper left, those are the terminals for the LED inside. But these are our output field device simulation. The first 3 are fairly large. I can't remember, they're either 22 millimeter or larger. The second one is the one that we already looked at. I believe that's 16 millimeter. That's a very friendly size. And then the third, those are just pilot lights, 24 volt DC pilot lights. So you can use those for output simulation. I will warn you though that the smaller they are, the less heat they can handle when you're soldering the lugs. The first 3, those have screw terminals, but the second 2 have solder lugs. One thing I really like about the one in the middle is the holes in the solder lugs are big enough that you can coax 3 22 gauge stranded wires into it, so that gives you better wire management. In other words, you can use those lugs to land more than one conductor. Okay, power distribution. Here we have a bulkhead connector. I'm only showing one, but usually when I build these, I solder 2 of them in parallel. So I would have 2 of those right there, and the reds would be connected together, then go to the toggle switch, and then the black just goes into the system. So we have a toggle switch that turns off 24 volts DC. We got a pilot light, and then we feed that to wherever the red goes, 24 volts DC for the controller, and the 2 plus commons. The black goes to all of the minus or commons for the minuses. Okay, now let's add some field devices, input field devices. I didn't show you the toggle switches, but this is what I use. These are mini toggles, not micro, but mini. I typically run the red or the positive to the center lug. So the 6 toggle switches switch the 24 volts DC into those 6 inputs. Now you notice there's more input. You can add more toggle switches. Toggle switches are dirt cheap. Now we add output field devices. I only show 4, but I recommend 6. And to be honest with you, but I definitely recommend that you do at least 6 and 6, if not more. Enclosures. This is typically the kind of box that I use. They can come with flanges or without flanges. They're really nice and heavy duty. They're easy to work with, and they come in a whole variety of sizes. This is the same box that I use, if you see it on the left there. You can see 6 of those round single pole, single throw momentary push buttons that are also the output LEDs. Then I have 6 toggle switches. Let's talk about construction. 2 tools that come in very handy for me, because when you're going to lay out the locations for the openings in your enclosure, you want the drill bit go in an exact spot, right where the crosshairs are. Well, these spring-loaded punches work real good for that. This other tool, a uni-bit, you can see the markings in there for different sizes. This allows you to drill a small hole and then just keep pushing this in until you get out to the size you want. The downside is if you're not paying attention and you wanted a 1/4 inch and you push a little too far, you're going to get something else, and you can't undo the hole. Once the hole's bigger, it's bigger. So there is a little danger using the uni-bit. Okay, wires and termination. I always use MTW, machine tool wire. It has a softer installation. It looks better. It's easier to handle. And I always use stranded and tinned. Very important. If you're going to solder, you want the wires tinned. And then I ferrule everything now. I use these crimp ferrules on anything that's not soldered. Now the switches, those toggle switches and the push buttons and lights, you're going to have to solder wires to those. But the wires are going to come out of your digital field device simulator and go to your controller. That's where you use the ferrules. Ferrules come in different sizes and colors. I always use 22 gauge wire, so I buy ferrules for 22 gauge wire. The crimpers, though, that's another story. If you look down in the bottom row, you see 4 different shapes. The first one on the left is probably the best, simply because it's more flat and it'll slide underneath a pressure pad underneath a screw better. And if you look at these crimpers, the first 3 give you everything but a flat crimp. The 4th one, which is the one I have, you put the ferrule in there and it crimps it nice and flat. The downside to that last one over there is $235 to buy the tool. If you're going to do a lot of crimping, you want that last tool over there. It'll last you a lifetime and you'll never be disappointed in your crimps. I want to warn you, even though this crimps them flat, sometimes if you pull on the ferrule really hard, you can pull it off. Well, don't pull on it. Put it underneath the pressure pad for the screw and then run the screw down tight, and that will put an extra little crimp on it, and there's no way it's going to pull out of there if you've got the pressure pad down tight under the screw. Terminals. Terminals can be inside the enclosure or they can be outside if you build one similar to what I do, where I use that digital field device simulator. Then I mount the controller on a piece of DIN rail, and then I use regular terminal blocks like you see on the right to expand or extend I/O out and off of the trainer to external things that I might want to hook up to it, like sensors and things for playing around with the system. The first one, the black terminal strip, those come in all different number of landings from 2 up to at least 12, maybe more. They're very inexpensive, and it's good to have a handful of those laying around. The one in the middle, I'm not real fond of those. Some people just love them. I'm not fond of them because I can't always see what the connection is doing. Terminal strip depends on how you're going to build your training unit. Inside of the units, if I need to manage the positive and negative bus, if you want to call it that, then I'll take a 4 or 8 terminal strip and then use these jumpers. That way I have 4 sets of pads for positive and 4 sets of pads for negative. You can put 2 ferrules underneath each screw pad. So that means in that 4 connectors or 4 screws, I can put 8 ferrules underneath those 4 screws. So this is a good idea. And by the way, you can buy these jumpers on eBay or Amazon. They're dirt cheap. Matter of fact, it doesn't even matter what color they are. The electrons don't know what color of insulation is on the jumpers. This is a micro 810. Notice that there's less terminal and there's 2 unused inputs. If you have an 810, you could go out to 8. The problem is you've only got 4 outputs, period. And although 4 outputs will get you by, as I said in the beginning, the 810 does not have Ethernet. The only serial port is USB. Serial communications. Well, 820 has those 6 screw terminals, and you notice that it's ground, transmit, receive, ground, data minus, and data plus. And this is the pin out. Now what I did, because the 820 does not have a conventional connector, I purchased one of these. I think they were $12 to $15. It snaps right on a DIN rail. And then I ran 3 conductors from G, TX, and RX over to the appropriate terminals on this terminal strip, and then I can plug a male or a female sub-D shell coming from my USB to RS-232 adapter. Or if you got an older computer, you have an RS-232 on it. This is my solution for just having screw terminals for the RS-232 connection to the controller. This is my development station for the 820. Now you don't have to do all this. So there you see my digital field device simulator with 6 in and 6 out. Coming out are blue wires, green wires, and red and black. Red's positive 24 volts. What you don't see are the 2 bulkhead connectors right above the words PLC Professor on there. You can't quite see them, but that's where I plug in the 24 volt DC power adapter. Then that 24 volts DC, when you flip the on-off switch on down in the lower right corner, that feeds 24 volts DC over to the controller and to the little HMI and to the inputs on the controller. Notice also that I'm using 6 inputs, but I have other inputs connected to those blue terminal blocks up at the top. Up at the top, that green terminal block is an extra output, an unused output from the controller that's not used for those 6 lights. The orange and the yellow is high-speed counter. Orange is high-speed counter, and yellow is analog output. Then there's 4 brown. Those also connect up to the same inputs, 0, 1, 2, and 3, that are connected up to this box right here, 0, 1, 2, and 3. What you have to do is you have to leave these toggle switches off if you're going to run analog inputs into those brown terminals up there. And then, of course, black is common distribution, red is plus distribution, and if I want, I can run a conductor from the group of red blocks into that fused block, and I can run fused power out to other devices. The little remote LCD, what that gives me is USB. Now, what you don't see over underneath of the 820, in other words, right below the 820, you see a yellow wire that comes around and then it curls back towards the DIN rail, and you can see some ferrules back there that aren't connected. Those are the RS-232 connections if you want to connect up that HMI remote LCD to those 3 connections, the black, the yellow, and the purple, that go up to the top to that DIN rail mount breakout. So you can pull those 3 ferrules out, put these 3 in. Now you can use the USB connector on that little HMI to your PC, and it's passed through. So right behind that white rubber cover, if you pop it off, is the USB. You plug into that, plug into your laptop, and if you've hooked up the 3 communication wires up to ground, transmit, receive on the 820, now that's your serial RS-232 USB connection between your laptop and the controller. But you still got the Ethernet. As long as you've got Ethernet, I can't imagine using the 232 unless you want to use that display. So If I want to do something with that little display, then I would disconnect the 3 conductors going up to the breakout board up there at the top. I would connect in these 3 coming from the HMI, and then I would do my little HMI project on that screen. It's a nice little remote LCD. I don't remember the cost. I think it's about $250, something like that. And that is the basics for the materials and the construction for building an 820 learning station. All this material and more is in this set of manuals. This says 2nd edition. By the time you watch this, the 3rd edition might be out, but the material's still going to be in there. Okay, so now you've decided whether you're going to build one or you're going to use a simulator. Building one's not a big deal. You don't have to go fancy like I did. You see in the background over my shoulder there, you see a bank of lights, red, green, 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 yellow, and blue, and you see the exact same configuration up over my shoulder with the control logics. Those are the PLC Professor field device, digital field device simulators. I've got all the toys because I'm just a big kid. Okay, so now you know whether you're going to build one or you're just going to use a simulator. And you can do both. You can start out using the simulator while you're building one. That'd give you the best of both worlds.